Today I'm here to present FAST-EQA, Efficient Embodied Question Answering with Global and Local Region Relevancy. First, to introduce the problem of EQA, given an unseen environment S and a natural language question Q, an embodied agent with visual perception capabilities must explore the environment to answer the context-dependent question using natural language and then stop when confident. This is also known as active EQA. For the question, it can be either multiple choice or open answer, spanning a number of different question categories. We assume that the agent has RGB camera and depth sensor inputs and moves by taking discrete steps around the scene and then turning. For the environment, we assume that it's a 3D environment, which is typically a single floor consisting of multiple rooms. Practically, this has a number of applications, for example, for robots deployed in human-centric environments such as service robots, office assistants, or in-home caregivers, and must respond to queries such as, is the bedsheet color in the master bedroom the same as in the guest bedroom, in which the agent, starting from a random location, has to explore to both bedrooms, look at the color, make the comparison, and answer the question. We survey a number of related works, notably Explore EQA, Memory EQA, Graph EQA, and Find EQA. Each of these methods uses a different focus when solving this problem. For example, stopping exploration based on conformal predictions of confidence, injecting hierarchical memory into each module, building an explicit metric semantic scene graph, or using a more fine-grained exploration strategy. Overall, however, current methods have success rates that are still lower than ideal deployable standards, and they're often not operating in real time for exploring. For example, there's a large latency after each step when deciding where to step to next. We propose FAST-EQA, and this is an overview of our architecture. It's based on a number of key design choices. First, we're inspired by how humans explore a new environment to find a target object or observation, and we try to model this intuitive exploration with prior estimates of relevant regions. We also leverage various foundation models with pre-existing knowledge for semantic guidance. And third, we have a bounded visual memory to retrieve answers from, which will not scale poorly when you have larger scenes or more rooms. Now for each component, for the global relevance exploration, the agent will use an occupancy map and scene morphology to detect clusters of doorways or openings using TSDF voxel fusion, and we model these as transitions between relevant semantic regions. The agent steps to each doorway or opening and identifies what room is seen using region identification. If a relevant region is seen and the agent is outside, it will step towards the relevant room using AM radio feature guidance. If the agent is already inside the relevant room, we transition to local exploration. In local exploration, the agent turns to essentially get a full panoramic view of the region and check whether it has enough information to answer the question. We then query a VLM for a stopping condition, checking whether to stop exploration and answer the question or to keep exploring. Finally, each RGB observation scene is scored with a relevancy score, which is a combination of a fine-grained clip similarity and a more holistic VLM confidence score. The top K relevant images for each visual target in the query are stored as a bounded visual memory throughout the exploration process. Images are then retrieved from this memory for final question answering using chain of thought prompting to a VLM. For our experimental setup, we evaluate across 4 benchmarks for a comprehensive evaluation. We do 3 trials across each benchmark to further quantify the variance between trials when multiple large language models and vision language models are used. We measure both QA success and path efficiency. From our results, we see that our method achieves state-of-the-art on HMEQA and ExpressBench. We achieve comparable results on multi-target HM3D and active EQA. More importantly, we evaluate on a subset of 100 HMEQA questions and measure the time for each exploration step with our method and other baseline methods. And we find that we achieve a 13.6% speedup over the next fastest method, making our method the closest to near real-time performance. We ablate key modules in our method as well as the size of the fixed visual memory. More details can be found in our paper. The main limitations of our method is that the system's effectiveness is bounded by the spatial reasoning capabilities of current VLMs, and we observe that the VLM we use exhibits variance across runs, sometimes producing inconsistent answers. 2 directions of future work is the development of latent visual memory representations to capture and compress scene information, and integrating structured spatial memory with language-driven reasoning. Thank you for listening. Please check out our project website as well as our paper on arXiv.